So, Despina, we're here at the Munich CADFM Conference 2025. You will be presenting on silicon photonics applications for transceivers. Could you please summarize the main messages of your presentation for those unable to attend?
So we all know that, especially with the advent of AI applications, the bandwidth demands are increasing tremendously. This means that we need faster and faster transceiver devices, which are still operating at low power consumption and in smaller and smaller form factors. This means that it is very important to optimize those devices, and especially in my talk I focus on modulators because it is a very important device of the transceiver. And as these bandwidth demands are increasing, it is becoming harder and harder to meet these strict requirements on the modulator performance. So in my presentation, I show how we do, me and my team, how we do the design and optimization of silicon photonic modulators, starting from their physical properties like waveguide, geometry, doping concentration, using numerical tools. And then we use these tools in order to predict the electro-optic response of the modulator and calculate important figures of merit, such as loss and efficiency. In the next step, because of course we want to optimize also in terms of bandwidth, we do the RF simulation using HFSS, where we can predict the modulator bandwidth and RF performance. In my presentation, I show that using silicon technology, typically we face bandwidth loss trade-offs. So as we try to optimize in terms of bandwidth, typically we increase our loss. This is something that occurs in silicon modulators because they utilize plasma dispersion effects, where some loss is inevitable due to carriers. That is why it is very important to show this design flow, because it is very important for the designer to optimize the device according to the needs of the application. In the end of my presentation, I compare silicon modulators to other material technologies such as lithium niobate. It is shown that silicon modulators cannot have as high bandwidth as, for example, lithium niobate together with low loss. This means that as we go beyond 800G, it will become inevitable sooner or later to integrate new materials such as lithium niobate. Nevertheless, we believe that even up to 800G application with proper engineering and proper simulation tools, we can still use silicon photonics. This is because silicon photonics is a very important technology that promises a leap in integration density, substrate size, and the yield, which is very difficult to match with other technologies.
Yeah. So you already mentioned that you address various approaches to transceivers, not only silicon-based solutions, but looking forward, what do you think are the main challenges when you go beyond 800G? So you mentioned loss issues, which is a very important topic. So in general, efficiency, I think, is becoming a very important topic. So what do you think, what should we expect from the near future?
So yes, this is a very good question. As we go, especially beyond 800G, the demands of the modulator performance become stricter and stricter to meet. So of course, yes, there is the efficiency, the high data rates that we need to achieve, but we also need to make all these complex functionalities to put them into smaller and smaller form factors in a power efficient way. So in the end, one needs to optimize not only the modulator performance, but also the footprint and the overall power consumption of the system. And this is really tricky, especially as we go beyond 800G. I believe that silicon technology is still a key technology to consider, and this is because it offers some unique advantages. And especially beyond 800G, I believe that one very important advantage is the monolithic integration with electronics, because then you can have very compact devices with small footprint, novel functionalities. You can co-optimize the modulator, for example, together with a driver in order to boost its performance. So I believe that silicon will still play a key role in the development of 800G and beyond optical transceivers. Of course, in terms of the pure modulator, I believe that yes, novel materials should be considered because silicon, as I mentioned before, it has this bandwidth loss trade-offs. And yeah, it is very difficult to operate silicon modulators beyond, for example, 200 gigabaud. So other materials are more ideal for the solution because they traditionally show much higher bandwidth together with low loss. Lithium niobate is, for example, one of those. So, of course, novel materials should be considered for next generation transceivers. But in my opinion, yes, next generation transceivers will be a complex ecosystem, maybe with the integration of novel material and functionalities into smaller and smaller form factors. So I believe there is bigger and bigger the need for co-integration techniques, advanced packaging, and so on.
So in all these developments that you've been following throughout the years, how important was to use simulation tools in order to make decisions and decide whether you prefer a certain setup or a certain solution for the transceiver?
Simulation is extremely important, of course, in my field. So, because the transceiver is a complex device which consists of several components, and as we increase the data rates beyond, especially 800G, we really need to push all devices into their limits. We need extremely low loss, power efficient devices. This means that in terms of photonics, even simple components such as couplers, waveguides, heaters, they all need to be pushed to their limits in order to achieve the optimum power efficiency loss figures. This means that in my group we simulate all photonic components, starting from the very basics such as waveguide, couplers, spot size converters, and so on, to the more complex like modulator or photodiodes. And I believe it is very important to have an overview of all the photonic components if you really want to push the devices to their limits, and not just use black boxes, for example, from a foundry, because you target a specific application and you know exactly what parameters you need. So for this reason, I believe that it is very important to simulate all the photonic components from scratch. And more, another important aspect is that even when you receive the chips from the foundry, there can always be discrepancies or different yield on each wafer. So it is very important to have an insight of your device, to have a very good simulation platform to understand where these discrepancies could come from. And it is not only important to build some devices that have a good performance, let's say, but it is more important even to build some robust devices and to know that even with some fabrication imperfections, they could still perform well and they are robust towards these imperfections. So yes, all in all, I believe that for this reason, simulation tools are extremely important, and Lumerical gives this opportunity to have a good overview and simulation platform for all the photonic components.
Yeah. So we were honored to follow you on this path of simulation-empowered development. What is your perspective on the added value of the ANSYS CAD-FEM ecosystem for you, for your progress, for your innovation?
I believe that the ANSYS ecosystem is very important for what we are doing. This is because especially the transceiver device is a complex device. And the whole ecosystem is not only just photonics, it is photonics, electronics, together with advanced packaging, RF, thermal mechanics. So in the next level, it is very important to bring all these functionalities into the same simulation environment, and not only that each designer optimizes, for example, the photonics or the electronic device independently, but to bring them all into the same ecosystem, because changes, for example, in the RF part affect also the photonics part or the packaging or the thermal. And I believe that ANSYS is a very important tool because it has all these different tools that unify all these functionalities. And like this, we can develop not only standalone photonic devices, but we can optimize the complete transceiver system using ANSYS ecosystem.
And speaking about the impact of silicon photonics on the development of transceivers so far. So what are really the advantages? Because you refer to other technologies that are also possible. So what are really the benefits of using the silicon technology?
Silicon photonics is a very important platform for next generation transceivers. This is because, first of all, we can use, so silicon is leading the electronic industry for years, so the same foundries that they have the mature equipment can be reused to fabricate photonic components. This means that we can have photonic integrated circuits fabricated in big wafers, like 300 millimeter, for example, with high yield and low cost. So this is very important for next generation transceivers because it optimizes the cost and the yield factor. Furthermore, silicon photonics, because of the high index contrast in silicon photonics platform, we can have very compact devices with small bending radius. And like this, we can realize very compact photonic integrated circuits. Another very important point about silicon technology is the seamless integration with CMOS electronics. This means that even monolithically, one could bring up together photonic and electronics, for example, RF electronics. So we could have modulators and receivers together with transimpedance amplifiers and drivers, all on the same substrate, on the same chip. And like this, we could, first of all, optimize our performance because we could co-design photonics and electronics together. And we could bring all these devices into a really small footprint. We could minimize, for example, wire bonding, and we could have a better RF performance. And we believe that all these integration capabilities that are found on silicon photonics are really difficult to achieve using other technologies.
When you speak about these changes for the photonics devices, and you could have a wish for the simulation tools, what would be something that empowers you to be more successful with simulations in your development process?
Yes, of course it is very important to have reliable simulation platforms, and Lumerical is a platform that the important about Lumerical is that it consists of different tools. For example, there are the optical solvers such as FD, for example, FDDD, EME. Then there is charge for the doping concentration definition and the carrier change. We have heat for the heat distribution. I also find interconnect, for example, very important because different designers design on different tools, but in the end you can bring together all these components that each designer has optimized into interconnect in order to build more and more complex systems. For example, in our case, we target to bring into interconnect the full 16 QAM, for example, transceiver model. And yes, I believe this is very important for the future to go towards this direction and combine not only photonic devices, but together with electronics, thermal dissipation, for example, packaging, in order to have a better overview of the full transceiver chip.
Thank you very much for so many insights into photonic simulation. So we learned from you how challenging that is to do simulations on photonic systems, and we got some ideas how we can improve in the future to even move forward.
Thank you very much as well.